Next up is Byron Bunker from the U.S. EPA.
Thank you, Drew. It's a delight to be here. I'm looking forward to this conversation. I should first acknowledge the work product I'm going to go through is a product of both the agency I work for, the Environmental Protection Agency, but also the U.S. Department of Transportation's National Highway Traffic and Safety Administration. This is a joint work product of our two sister agencies. I want to start by talking about the program in summary. What does it accomplish? What do we see in this? And so this talks about it in a few metrics, and these are metrics I'm going to use throughout, so let me take 1 minute to explain them. The program starts with model year 2014 vehicles, and so when we talk about the value of the program, we make a comparison of it. We look at the first 5 years of production, so 2014 through 2018, and we take those vehicles and follow them through their whole life, through a 30-year window, and look at the performance that they would achieve compared to if that fleet were made up of vehicles only at the 2010 performance level. So if the products that were produced in 2010 were a static product and produced into the future, and take the difference. When you look at that difference, it's about 500 million barrels less of oil consumed. That's about 270 million metric tons less of CO2 produced. And that represents about $50 billion in savings in the U.S., and that's at about $3.50 a gallon, 75 euro cents per liter, roughly, fuel price. The estimate of the cost for the additional technology on the vehicles is about $8 billion. So then that's a net savings to the community, to the trucking community, of about $42 billion. When you look at the social cost of carbon, the other impacts of this legislation, it's about $49 billion in net benefits. Part of what I want to do in this presentation, one is summarize what the program is itself, and then secondly, talk about a few key points from it. And one thing I should say, and I know this group will be very interested in the whole broad spectrum of energy policy and transportation policies. The U.S. EPA has a separate program, the Smart Way program, that's very focused on best practices, on driver training, on educating fleets, on helping fleets to operate logistics more efficiently. I'm not going to talk about that program today other than to acknowledge it's an important part of the solution. And secondly, to say much of the technical work that goes into the engineering part of this comes from the experience of that team. That team started in 2004, has been working on many of these issues. If we want to look at a sort of political timeline, or real timeline from what comes from this work, there are three major events, effectively. First, in March of 2010, the National Academies came out with a study that Mike Jackson described earlier today, and that was a precedent for much of the work that he talked about. In May of 2010, the President took the Secretary of Transportation, the Administrator for EPA, together at the White House in a ceremony and directed the two agencies to work together to come up with a proposal for the Department of Transportation to address fuel consumption and for the Environmental Protection Agency to address greenhouse gases. This August, that final action went into place with the signature of the Secretary and the Administrator. The memorandum that came from the President laid out a few goals for our program, and it really did dictate much of the work. It said we should look at existing technologies. It said that we should look at segments of the market and look at special opportunities there. That was basically something that would be common to all of us, is look where the biggest opportunity is, look for the lowest hanging fruit, be sensible. It says take into account the market structure, and really to, in some ways I've interpreted that also to mean first, do no harm. When you look at how the market works, the way it's grown to service this market, make sure that the programs that you add, you don't push away from that, you don't change that impact. That you seek harmonization, and that's fundamentally part of the reason to be here today. That it's important to remember that these products are produced often internationally, that we can harmonize on methods and procedures, and that's a worthwhile endeavor for all of us. And of course, in some ways, especially for Europe and the U.S., since Volvo, Daimler, PACCAR are very much represented in both markets. In special importance in the U.S. was to pay a particular focus on the leadership that the state of California has shown to make sure that they're part of our entire process. The rule, often when I've talked about this rule, I've talked to audiences that understand our light-duty corporate average fuel economy program. I think for this audience, maybe some of these things are almost self-evident, but commercial trucks are far more complex than cars. And addressing them in a logical way takes a much more complex solution. The program starts very early. That's unique. Starting in 2014 is not typical, and that could only come through the collaboration with the industry. And it also comes from looking at the President's directive to think of this program in terms of existing technologies that could be more readily used. You can't have a program that starts as early as 18 months from now and have that happen in the context of a program that's looking far into the future and into advanced technologies. So it's very focused on getting existing technologies off the shelf and onto these vehicles. And because of that focus, because of the broad stakeholder outreach into the program, it's been broadly supported in the U.S. We have a very good and collaborative relationship with the regulated industry. The trucking community is represented by the American Trucking Association, had sought this kind of regulation in the past. They saw this as an opportunity to put pressure on the manufacturers to make better products for them, and the NGO community was also quite supportive. This slide is just meant to be a reminder that the program that I'm going to talk about covers all kinds of heavy-duty vehicles, effectively all vehicles over 8,500 pounds gross vehicle weight rating. So that's pickup trucks, that's delivery vehicles, that's a wide range of products, all the way up to articulated combination tractors. This is sort of a tick list of the rule. I'm going to skip over this slide, and I think I will do that several times today. The organizer is going to make the slides available. They hopefully are a useful reference to you, but I want to get to some main points, and so I will skip this slide and talk about first. In doing this, we have broken the program into 3 distinct categories, and this is the first one I want to talk about. It's Class 7 and 8 line haul tractors. In this segment, we do a couple of things. First, we regulate engines and tractors separately. And as we go through this, I'm going to talk about some reasons for that. Engine standards are met through the same procedures and processes today for NOx and particulate matter. When manufacturers run and comply with our criteria emissions program, that test procedure, those test results are used to show compliance with the engine CO2 standards, with the engine methane standards, and with the engine N2O standards, the nitrous oxide standards. So in that way, it adds no additional test burden. It's a straightforward and consistent system for both us and the manufacturers. The tractor standards are met through a compliance model. This is something very different. We call it the greenhouse gas emissions model. It's a typical model describing truck physics. There's any number of models that we could have used, and I'll talk a little bit later about how we chose this model and what it means. And I'm going to talk in some detail about why this model only incorporates a few technologies. In many ways, our look at this is maybe even thought of as small-minded. Certainly, it's at some level a small first step, and I'm going to talk about why we made those choices and how we made those. But before I do that, let me just talk about this segment itself. On the upper right-hand side of the picture, you'll see a table that grids into 9 different tractor categories. We set unique standards for Class 7 versus Class 8 and Class 8 sleeper cabs. So there's 3 different categories in that, going left to right. And then there are 3 different categories based on low roof, mid roof, and high roof. So that makes for 9 total. I think it maybe in the picture is self-evident to you. We see tractors built in these 3 different configurations, these 3 different roof heights to match the trailers that they pull. That's for aerodynamic reasons. It's almost self-evident, I think, to the engineers as they look at this. And then, of course, the sleeper cabs are done for the truckers that need to have an hours of service criteria, that they basically use the truck as a hotel room. In setting these standards, we set 9 different standards, and I want to talk for 1 minute as an example of the kind of choices that go into these programs and why sometimes our first idea isn't the one we end up with. It's typical for EPA to set standards that are met on an average level, to assume that some products will do better, that some products will do worse, that gives manufacturers ability to service a market and service needs, and also flexibility when they introduce new products. So it would have been typical for us in our starting point to pick a single standard for this mix of tractors and then tell manufacturers they can comply with that standard by averaging to it. And so that was the start of our discussions, and initially that was something that both us and the regulated industry thought was a good idea, that was just flexible, that was simple. But as we thought about it and as they went and talked to their product planning teams, both of us realized, I think, together a problem with this. And that problem is the sales mix varies significantly year to year. You'll have years where the grocery store chains have money and they're buying day cabs that are used in spoke and delivery service. You'll have other years where the long-haul tractors are the predominant purchased items. And if in each of these squares you have a different sales mix every year, but a fixed standard, your ability to comply with that standard gets very complicated. And so to simplify that, by having individual standards, it doesn't matter your sales volume in any one of these blocks. So what we've done by setting individual standards, it means your sales mix sets your corporate average standard, because if you don't sell any, you don't have to show any compliance in that one box. We then take that idea of 9 separate standards, and we do allow averaging between these, and we do allow those averages to be carried through a 3-year time window. So that gives the manufacturers additional flexibility, and it ensures that as market swings come and different customers have different needs being met at different times, that they're able to handle that transition through time, as well as product launches and the difficulties that come when you're introducing many new products at one time. The second thing, if you look at the bottom right hand of this table, of this slide, you'll see a table that lays out percent reductions, and I'll have the absolute values later, but I think they're sometimes a little bit hard to speak to. It's easier for some people to think of this as percent reduction. So again, these are compared to the 2010 performance, and these are based on the standards that we set. They are absolute standards, not relative standards, but absolute standards. And you'll see that they're quite different. The largest reduction comes in the bottom right-hand corner. That's the high-roof sleeper cabs. That comes for a couple of reasons. One, they have the highest average speed. The average speed assumed in our drive cycle for those tractors is about 110 kilometers per hour, and that's almost 85% of the drive cycle. It has a transient mode. It has effectively a 90-kilometer cruise as well, but the dominant assumption for those tractors in the U.S., and is represented by the data in the U.S., is 85% of the time at 110 kilometers per hour. So you get a very large benefit from aerodynamic improvements. That becomes the dominant port. Secondly, because they have idling needs, they have hoteling needs for the tractors, the use of a diesel APU or another means to supplement or replace the engine for overnight idling provides a big reduction. If you go all the way over then to the upper left-hand corner, the low roof day cabs, the ones that are servicing often regional haul or often even more local than that, you'll see that we have a projection of only a 10% improvement. In part because it's a different drive cycle, so aerodynamics give you less benefit, in part because there's no hoteling idling to eliminate since they don't have the sleeper cab, and in part because of our assumptions about technology. In setting those standards, we assumed that 40% of the vehicles in that category, so 40% of a manufacturer's production volume in those boxes, would not have any aerodynamic improvements, that they could continue to be what we would call a classic cab. That's almost by definition in the U.S., that means a lot of chrome on it, and that means that it has a big frontal area, a very large radiator. We did that reflecting that a lot of those vehicles are used in gravel haul and other very high load applications where the large radiator volume is needed because the speeds are very low and they have a high cooling demand from the engine because they have very high power demand. Also, much of those work in off-road operation, and when you work off-road, you're likely to damage aerodynamic fairings in the first place. So in setting those standards, we gave consideration to that a significant portion of that market would not be served well by aerodynamic fairings. And not least of all, as far as the environment's concerned, adding weight to the tractor that doesn't provide value when you could be putting that weight in the back of the truck as payload is a mistake. And for most of these vehicles, ones we're talking about, they are at their gross vehicle weight rating when you're hauling gravel, when you're hauling other commodities like that. So we've taken that into consideration as we set these standards. If we go to the next slide. And I may have done this a little bit out of order because I'd like to talk about how we came to decisions, why we made the choices we made, and a lot of that has to do with where we were and where we went. And when I see presentations on the Lot 2 study and the work that Gratz has done, I see it is very, very similar to where we were about a year and a half ago, 2 years ago. And that as we were doing our work, I think engineers come to these things in very, very similar ways. And so there was two things that really, almost from the start, were part of our work. One, we took the work that the Department of Energy had done in doing energy audits and looking at where is the energy used in a tractor. And if you look at the work that's done for the Lot 2 study and other things, you'll see that the breakouts for the U.S. trucks and the European trucks are not so different. Where does the energy go? As a caution to the non-engineers in the room, if you look at those, you'll see a little bit very different looking numbers. That's only because of what the comparison is. Many times you'll see pie charts that only look at where does the brake work from the engine go. And if you look at it that way, about half of the energy goes into aerodynamics. If you look at it where you include the losses on the engine, almost 60% of all of the losses are heat losses from the engine, either to the coolant or to the exhaust. And then when you redenominate on that form, then you see aerodynamic losses of 15 to 20%. That's the same as the 50% number that you might commonly hear on a brake-specific basis when you look at it from brake power from the engine. So as engineers, you look at this and you say, where are our biggest opportunities? And it's very plainly aerodynamic improvements, engine improvements, tire rolling resistance improvements, and then you get to accessories, and then you get to a few other things that seem smaller and smaller. So our first thing is, let's look at those big opportunities. I think that's a normal thing. Secondly, it was clear to us very early on we need a modeling approach. Let's start with a systems model. Let's start with something that models this because we can't test all the vehicles. That'll never be a possibility. So we began working on a modeling construct, and that modeling construct came straight out of the energy audit. Let's follow all these paths and add them in. And again, when you look at those, the work that's been done for Lot 2 is, in my mind, excellent work and very consistent. And so what I want to kind of walk through then is, how did we start with similar work to that and make decisions, policy decisions, in order to implement a program? And one thing I don't want to have the, I think I've expressed to Christoph and some of the commission staff how I almost envy them the opportunity to revisit these decisions. Decisions are always made with the information you have in that day, and I'll talk about why we made the choices we made with the information we had. When you wait a little bit longer, you get more information, you might make different choices. So I don't want to imply that these are necessarily the right choices here. There'll be choices made with the information that's available, but I do want to explain why we made choices based on what we knew in the time. So if we can go to the next slide. One of the first things we did in looking at this was decide what technologies are we going to focus on. So I mentioned before aerodynamic profiles and fairings, reduced tire rolling resistance, weight reductions. I'll talk about how each of these come in as a regulatory construct, vehicle speed limiters, and reduction in extended idle. If we go to the next slide then, I think almost as important is, why did we leave out some things? And I should say, leave out some things that were very important to our engineering team. I frankly have some staff that have never quite forgiven me for some of these choices. One of the first one is, why aren't we looking at gearing and engine power in the match of the vehicle? Those synergies are fundamental. Those synergies can mean 5 or 10% difference if you get that wrong. And that means, do we have the right transmission gear ratios? Do we have the right drive axle ratios? How does the tire size, so we have a final drive ratio? And how do those fit into the power profile for the engine and then the fuel consumption map for the engine? That whole question was a fundamental part of our initial work. We did a lot of work at how do we discretize an engine model? Do we need a 30-point map, an 80-point map, a 130-point map? And do we need to compensate for transients? And what do we do with all of that? And in the end, we decided that we weren't going to touch that. And in part because customers already do that, right? And they do that in the tool I'm most familiar is the tool that Daimler uses, but all of the OEMs in the US have similar tools. If you go into a Detroit dealership to buy an engine, And when you ask them so, they will take you and sit you down with a software tool, and they'll ask you some questions. They ask you, what payload do you carry? Are you carrying potato chips? Are you carrying electronics? Are you carrying steel? What are you carrying? They'll ask you what route you're going to run. And if you tell them I'm running from point A to point B, they have a GPS map of that route, and they'll know two things from that. They'll know the average speed, the speed limits for the whole route, and they'll know the grade changes. And then lastly, they'll ask you, do you want a vehicle speed limiter? Will you set, as a fleet, set a vehicle speed limiter? With those pieces of information, they'll run an optimization program that's basically another truck model, similar to any other truck model, that will select the best engine and gear match for fuel consumption in a reasonable number of shifts. As Mike said earlier, in the U.S., these are all manual transmissions. If you have excessive shifting, if the driver has to shift every few seconds, they won't. They'll just run a gear down. If they run the gear down, you have a big fuel consumption penalty. So the software tool will optimize those choices. That happens already. It's very efficient. And we had a very strong concern with us setting a standard that was based on something else. If we set a standard, we would have had to pick a single drive cycle, a single average payload, and an assumption about grade. And those assumptions would have not been right for any fleet in the U.S. They might have been right for the whole country in aggregate, but they would not have been right for someone running in the Rocky Mountains versus the Plains versus the East Coast. It wouldn't be right for the potato chip haulers, the Frito-Lay company, nor Coca-Cola distributors, nor the heavy steel carriers. And so by leaving that to the market, we don't have this problem of someone coming to a dealership, running the dealership's model and being told this is the right truck, and then running the government's model and say this is the right truck, and those be two different answers. That was not acceptable to us, and we think that would have been the wrong thing. By taking those elements out, we take that dichotomy out. We don't have that trade-off in front of us. If we go to the next slide then. And I'm going to go through some of these very quickly. We have a number of, sometimes we call them flexibilities, sometimes we call them exemptions. They're pieces to deal with particular parts of the fleet where it wasn't, we didn't think appropriate to set a standard, or the standard should be based on a very limited set of technologies. And so we have exemptions that take vehicles that predominantly work off-road, that are very high weight limited, vehicles that are used in vocations where they're very much stop and go, and where, again, aerodynamics may not make much sense. So we have a number of exemptions that bring those vehicles into the program. If we go to the next slide. These are the actual standards. They are expressed in grams per ton mile in the CO2 space, and in gallons per ton mile when you talk about the Department of Transportation's program, which is exactly parallel. CO2 and fuel consumption are one and the same in this program. Only offer it as a reference to this piece, and then to talk about one bit of policy that comes to this, and just to highlight it. In setting these, we assume an average payload. You know, my whole concern I just had, because we take that out, we do have an assumed average payload for each of these categories. We have assumed drive cycle. The drive cycles are different, but there's assumed drive cycle. There's no grade. The reason, given all of those assumptions and those fixed values, it would have made no engineering difference if we'd have done this in grams per mile or grams per ton mile. The reason we did it in grams per ton mile is to communicate to the public. This way, the largest, most efficient vehicles for hauling freight have the lowest number. The smaller vehicles that are carrying less payload have the highest number. If you do it in grams per mile, you get just the opposite. For the industry complying, for us regulating, it would be no difference in this construct. But in communicating to the public what happens, it's important to emphasize that larger vehicles are more efficient in hauling freight, so let's have a program that reflects that reality and communicates it well to people. If we go to the next slide, please. The simulation tool is available from our website. You can download it. There's actually two versions. There's a version that's open-coded MATLAB Simulink. Someone can take that, reverse engineer it, explore it, understand it any way they want. There's also an executable version that anyone can run. You don't need a software license, and you can use that tool for showing compliance and just seeing the results you would get. If we go to the next slide, please. That executable version is set up so it can be run in a batch format, so manufacturers can submit all of the different configurations of vehicles they produce, have it run in a batch form, and have results given for every different vehicle. Let's go to the next slide. So there's, as I said, only 5 things you can change about vehicles. One is aerodynamics. Aerodynamics comes in as basically a CDA number, a force number, coefficient of drag times the frontal area of the vehicle. We have that come into the model through a bin structure. It's just highlighted bin 1 through 5. What the bins are is frankly a very coarse measuring tool. The ability to measure aerodynamics very, very accurately is frankly quite difficult. There's significant variability. And if manufacturers came in and tried to differentiate from very small variations, frankly, it was expressed to us a number of times that each manufacturer at some level was concerned that the other's implementation of the test procedure would be slightly different. Because it would be slightly different, the result would be slightly different. Since the results would be slightly different, one might be advantaged or disadvantaged in the marketplace. By taking it and making it a relatively coarse instrument, those fine gradation differences in how it runs become less relevant. So think of it as a relatively coarse tool to take the coefficient of drags and break them into five bins. If we go to the next slide, please. Even for low roof day cabs and sleeper cabs, when we looked at those tractors, it was actually, I think, an education for us and a reminder to us both about the volume production for these products and that they don't get the scrutiny we all assume. In doing the work, originally we had the same 5-bin solution for the low roof tractors. And that made sense to the engineering teams we were working with the truck OEMs. They went back then to their aerodynamics departments to say, does this work? Does this make sense? Or are we going to be whole? And they came back and said, we don't know. In reality, they spend a lot of engineering resources on the high roof sleeper cabs because that's their highest volume product. That's the one that runs at the highest speed. That's where engineering resources are best spent. For their low roof products in the U.S., those are simply the high roof product with the top fairing removed. So effectively, they were saying, we don't really spend time engineering the best aerodynamic solution for those. And there's one more reason. Besides low volume, it's not that important as it is for the high roof. It's also their trailers are often different. A flatbed can be carrying almost any kind of product on it, so what do you optimize for what's on the flatbed? And optimizing for a tanker can also be very difficult. So it didn't make engineering economic sense. For that reason, we decided to effectively break this category to just 2 bins. Either no aerodynamics, a classic tractor, or one with aerodynamics that carries over the same frontal treatments that the high roof sleeper did. And so it breaks it only into those 2 categories for these products. If we go to the next slide. The other thing to say about it as far as a test procedure, we have a coast-down test procedures that's used to determine the CDA value. That coast-down test procedure is that it works, it's effective, it's highly constrained to get good results. That means it has very stringent limits on average speed, on road grade, on road conditions, a number of things that set that. Given that, it's difficult to imagine someone can do that for all their products and all their variations. So what we wanted to do was leverage the engineering work that the manufacturers already must do. And so to have that leveraging, to take the advantage of that, we say, take one of your own vehicles, the vehicle you know the very best, your own internal golden vehicle, the one that you've done CFD on, the one that you've put through a wind tunnel, the one that you have the most on-road experience. Do a coast down of that and then correlate your engineering tools to it as a reference value. And then that correlation, that factor that relates our reference test procedure to your CFD tool, to your in-house wind tunnel, to your contracted scale wind tunnel. And then you can use results from those test procedures on other vehicles through the correction factor as a way to show compliance. And that way we leverage the engineering work that goes into designing the vehicles and don't require aerodynamic testing on a coast-down procedure for multiple configurations. If we go to the next slide then. The tires come into the program through an ISO test procedure. I think that will be straightforward. I won't talk about that. But let me talk for a minute about weight reduction. Weight reduction, initially we wanted to do, as you would do in any other case, what's the mass of the truck, what's the curb weight of the vehicle. And we ran into two problems with that. First, the variation in curb weight was, for many of these tractors, 8,000 to 10,000 pounds. 3, 4, 5 tons difference between different tractor configurations. And we started trying to ask which of these is right, which of these is wrong, which of these makes the right baseline. No one knew, because usually those were actually serving some customers' real need. And so we found no way to come up with a baseline weight. We found no way to say what was a reasonable weight and no way to come to that. But we all knew that removing mass was good. It's the same value as for a passenger car. If you accelerate and decelerate a mass, you're throwing that energy away. If you take that mass out and you put it as payload, that's an efficiency improvement. So to bring mass reduction into the program, we looked at it as a technology. If you replace steel with aluminum, if you replace steel with high-strength steel, we assume you're already going to do that as efficiently as you can. We have engineering estimates of the value of doing that for particular components, and that becomes a lookup table. You say, I've replaced this component on this tractor, that is worth 5 kilogram reduction, that 5 kilograms goes right into the model. That's full stop what you do. It's simple, it's easy to implement, it's easy to enforce, it gets the right motivation, and it doesn't cause us to go and start asking what's the right solution for each customer, because the mass that was being added was mass for utility the vehicles needed. Vehicle speed limits, actually I'm about out of time, so I'm going to skip vehicle speed limits, idle reduction, or other two technologies that come into the program. If we go to the next slide. We have a program for pickup trucks and vans. These are a big part of the U.S. market. I think maybe a surprise to many of you here, half of these are gasoline vehicles. If we go to the next slide, we express that standard versus a work factor. That work factor effectively is a vehicle attribute that looks at its payload capacity. Does it have to carry extra mass because it's four-wheel drive? And that's utility that's needed, because often these are used in agricultural settings where they have to pull a trailer off-road, and so they must be able to have four-wheel drive to pull away from where the animals are kept, where livestock is kept. And towing capacity. By relating it to that, we had a factor that related to the utility of the vehicle and respected the way the market already provided those vehicles. They're already tested on the chassis test procedure, so I should be very plain. This is a chassis test procedure of the whole vehicle. And that chassis test procedure takes in half payload is determining the test weight. So the reason that the graph goes from lower fuel consumption or CO2 to higher as the work factor goes up is primarily not because of technology differences, but because the test weight went up. The test weight goes up because we want to evaluate these as they perform. Their emissions therefore go up directly. And by doing this, we don't incentivize the selection of low utility or high utility or any utility. We're agnostic to that, and you continue to offer a range of utility needed by the market. We spent some time figuring out what to do with pickup trucks and vans. They're a big part of the U.S. market. We have a test procedure for them already. It was an important piece. We spent a lot of time on tractors because they are a very big piece of the fuel consumption puzzle. They're a big piece of the opportunity. And then we were asking, what do we do with the rest? And we spent a long time trying to define what the rest was and how do you use the rest and what's important for the rest. And there's lots of opportunities here. Straight trucks are a big part of this market. These utility vehicles, I think they were called bucket trucks in the presentation from Mike, there's big opportunities for hybrid applications there because they idle all day so that hoist can operate. If you run that hoist off a battery or off of some stored energy, it's a huge savings. It can be very, very substantial. At the same time, trying to regulate this segment was very complicated. And after going around and around on this, we came to the conclusion of two things. One, we couldn't define what this segment was, so we defined this segment by what it's not. This segment is defined, I'm not a tractor, I'm not a pickup truck, therefore I'm vocational. So everything that's not in the first two is in this. Secondly, if we go to the next slide, we decided to regulate these based on what they are. What they are is, at a base, what they all have in common is they're all body on frame, they all have an engine, they all have tires. And by looking at it just in terms of the chassis, we regulate only the biggest manufacturers. The Freightliner brand, the Ford, General Motors, they provide the bulk of these products in the U.S. There are literally hundreds, and I understand in Europe thousands, of bodybuilders that add coach bodies to these, add all kinds of different bodies to these. Those people are not regulated in this program. The engines have a standard. They use the same test procedure. They're made better. The vehicle model that we described for the tractors is used, but there's only one input to that model. It's tires. So this encourages tire improvements. Again, just as an anecdote from this program, when we first did this, when we first started discussing this with the industry, the first question that came back from the tire OEMs was, none of us know the rolling resistance of our tires. So despite the belief that the market was already driving these improvements, no one was even bothering to measure. And anyone that's worked in a factory and in quality over the last 20 years know the first thing you do if you want to improve is you measure. If you have a metric and you measure, you'll improve. So we think in many ways, simply by having a program that makes the manufacturers measure tire rolling resistance for these products and bring that in, we will see an improvement. If we go to the next slide then. We have a program that incentivizes technologies. I think I'll leave that and go to the next. I think this is the last I will really speak to, and that's just to say we didn't regulate tractors, and that was, I think, offensive to a lot of our stakeholders. Trailers. Trailers are a big opportunity. It's relatively simple technology. Side skirts, small treatment of the back can get you big improvements. It's right there available. So why didn't we take action? It seemed we almost must have. The main reason is the test procedure. These products are made, they're relatively cheap. They're about $20,000 in the U.S. They're produced by, frankly, not very sophisticated manufacturers, and many of them are quite small. And they're different. They're different enough that you need a test procedure that can discern differences among them, and everyone wants something that's a real test procedure that really values their design improvements compared to somebody else. The only procedure we have right now is a coast-down procedure that, frankly, I believe at this point would be too timely and too costly for this industry to reasonably do on the diversity of their products. A wind tunnel even makes it worse. So we have to work with this industry to find a cost-effective way to measure their performance. Once we have a cost-effective test procedure, and I think someone said it earlier, you can't have a test procedure that costs more than the manufacturer of the product itself. That doesn't serve anyone any good. Once we have a test procedure that can value these, we will come back and regulate trailers because there is a big engineering opportunity here. If we go then to the next slide, this just gives back, and like I said, these will be available for reference, the cost and the payback on a per vehicle basis for the program. And then I'll end here. On our website, you can find the documentation for the rule. It's more than 2,000 pages of just the text that we produced, plus references to a number of other products. I would guide you to two documents. There's one that's called the preamble. The preamble document is sort of our statement of why we did these things, our logic, where that is. That's a good starting point. But also, if you look further down the page, you'll see something that's called a summary and analysis of comments. By regulatory process, we put out a proposal, and then we get comments from the stakeholders, the regulated industry, the NGOs, the whole community gives us comment. And by process, we collect all of those, summarize all the comments, and then give the agencies reasons for agreeing with the comment and making a change, disagreeing with the comment and making it. So our record of how we made decisions is contained in there, compared against the issues, the concerns, the questions that were raised by the community. So if you have a question, if you say, I don't understand why this was done, almost certainly someone else had that same question during the process. If you open that document, it's 700 and something pages, and do a search on a phrase that matches your interest, there's a good chance someone gave us that very comment, and you'll be able to read the reasons the agency took the decisions it did. And then lastly, I give you the contact information for our team leader. Angela Cullen did the bulk of the work on this. She certainly coordinated it all. She knows where all of it is. If you send her an email, she'll be glad to help either find the person that can answer your question or answer it directly yourself. And thank you for your time.
Thank you very much.